So real numbers are the only numbers that we're going to deal with in this class. And it's made up of several sets of numbers. Now, natural numbers are the numbers that you learn when you first learn how to speak. You know, you use your fingers, and 1, 2, 3, 4, and so on. Just natural numbers, the numbers that occur by counting. Then you have a set that actually includes natural numbers, which is the natural numbers plus 0. Now there's a symbol for natural numbers that you'll see, and it's this kind of capital N that has, it's not quite bold because it's not filled in, but it's not quite a regular one because it has this little outline to it. That means natural numbers, and if you put a 0 with it, you get whole numbers. Now 0 you think is a kind of a natural enough number, right? But the concept of 0 has been around, right? Nothing. Everybody understands that. But if you look at Roman numerals, for instance, there's no 0, right? You have I for 1, you have I for 3, X for 10, and so on. There's no 0. So the use of 0 is actually a relatively recent addition to numbers. It comes out about 1 millennia ago, about 1000 AD. For a number of reasons, they started using 0. So we call those whole numbers. Now, if you put a sign in front of whole numbers, so you have things like -2, -1, and so on, we call these the integers. And so I'm a big fan of answering numbers with integer, or answering questions with integers. And so integers have the have this symbol Z that I'll write on the board. And so those are all the numbers that are nice, round, easy to write. They have an exact value. They can be positive or negative. And so if you take ratios of integers, we have a rational number. Okay, so if you have a number like 2/3, that's a rational number. Now, rational in this sense isn't like, you know, when something's rational, it's sane. You know, it's not that context of the word rational. It comes from the word ratio, right there, the first 5 letters, and so it's a ratio of integers. Now, just because a number isn't represented as a ratio doesn't mean that it's not a rational number. So all natural numbers, all whole numbers, and all integers are rational numbers as well, because you can represent them as a ratio. For example, the natural number 3 over 1, is exactly the same number, it's just represented differently. 3 by itself is a rational number, because it can be represented as the ratio of numbers. So that's different than saying rational numbers are represented as fractions. They're not. The fact that they can be represented as fractions make them a rational number. So if I take all of these numbers and add in irrational numbers. Now, irrational numbers aren't crazy numbers. Well, perhaps you might think they're crazy, but these are numbers that cannot be represented as ratios. Like pi, for instance, the ratio of the circumference to the diameter of a circle is 3.14159, and it keeps on going. It never repeats, it never terminates. Pi has an exact value, we just can't represent it as the ratio of two integers. And so we call that an irrational number. Same thing with the square root of 2, roughly 1.141, and it keeps on going, never terminates, never repeats, so that's a rational number. There is an exact number. Now, I would prefer you always answer a question as the square root of 2 rather than 1.141, because no matter how you round it, you know, your calculator might give you 13 digits, it's still an estimate of what the square root of 2 is. The square root of 2 is an exact number, so we answer it that way. Okay, so with those sets of numbers, rational and irrational numbers, those are the real numbers. Now, we also have other numbers, and we call them imaginary numbers or complex numbers, and these usually involve the square root of -1. Now, this is not a real number in the sense that it's not an irrational or rational number. It's a number that is defined separately, and we call those a different kind of number. And we aren't going to deal with imaginary numbers at all. Even when we get into, let's say, quadratic equations, you know how you can get an answer through the quadratic formula, you have an imaginary solution. We'll just acknowledge that it's not a real number. We won't go any further than that. Imaginary numbers for what you're doing really don't have any particular application until you get into higher math, and then at that time you'll get familiar with them if you choose to go on that far. Okay, so those are number sets. Real numbers is what we're going to be dealing with. And so the distinction here with the real numbers is that real numbers are all the numbers you can put on a number line. Integers have just a natural number with a sign in front of it or a zero. Natural numbers are just the ones that you count. So these are the three most important sets that we'll be talking about. Okay, so let's, one of the ways that you know that something is a real number is that you can put it on a number line. And so you've all seen a number line, I'm sure. It's just a line with an origin, 0 in the middle, and you count up and down. And so all numbers can be placed on there, like -1/2 would go approximately there. Something like e, which you may or may not know about, is 2.71. That would be there. Pi, which is 3.14159, goes about there. Now, you can never graph things exactly, right? It's always the width of your dot. There's that uncertainty at best. And so any number that you put on the number line, though, is a real number. You can't, for instance, put an imaginary number on there. Like if you had 1 plus I, where would that go? It doesn't go on the number line. You'd have to put that on a plane, not on a number line. So it's not a real number in that sense. Okay, said 0 is the origin. And let's say you have two numbers, A and B. Just choose any two. The thing about the number line is that it describes an order of the numbers. You can have two numbers exactly equal, or a real number, if it doesn't equal it, is either greater than or less than a number. Okay, and that may sound trivial, but an imaginary number, you can't say that about it. You know, is 2 plus I larger or smaller than 3 minus 2I? You know, it doesn't have that kind of comparison. Here, with a real number, it has that property that you're either equal to it or it's greater than or less than it. Now, I wrote those in opposite order, where you have you know, A is less than or equal to B, or B is greater than or equal to A. These have the same meaning. Okay, so we're not real fussy about, you know, which side. The small one doesn't always have to be on the right. You can turn the inequality around and have the larger one on the right or left. Now, the thing about additive inverse is you would think of this as just the negative of a number. Okay, so the additive inverse of 3 is -3. The additive inverse of -3 is 3. It's when you add a number plus its additive inverse, you get 0. Now, a lot of people, and in fact your textbook will call it the opposite, that the opposite of 3 is -3. And in a sense it is, but it's easy to confuse that with the reciprocal of 3. Is the opposite of 3 1/3? You know, if you're really in a multiplication mindset, you may be tempted to call it the opposite. So it's, in my opinion, it's better just to use the formal name, the formal words for it. Additive inverse sounds so lofty, but it's very simple. It's just it's the number that when you add it to the original number, you get 0. Okay. So we don't confuse it with the reciprocal. Now, there's this other function that we'll talk about, and it's called the absolute value. And the absolute value just gives you the positive version of whatever's on the inside of the two vertical lines. Absolute value of 5 is 5. Absolute value of -5 is 5. Absolute value of 0 is 0. Now, one of the ways that I suggest you start thinking about the absolute value function is that think of it as the size of the number. You know, 5 and -5 are definitely different numbers, right? But there's a sameness about them, the fact that they have a 5 in it. it's kind of like the size is probably the best words, or if you start to get in a little bit more lofty math, they'll call it the magnitude of the number. But think of the absolute value as the size. When we deal with absolute value equations and how to manipulate them and everything, if you think of, I'm looking at a size of a number that's inside of those two lines, that'll be a very helpful way to connect a physical meaning to what the absolute value is. Okay, and then, and it's always positive. So, it's not always positive, it's always non-negative, meaning that it's either positive or zero. So if I were to measure this desk, or I would pass out some measuring tapes, and I'd say measure the desk, some of you would go left to right, others would go right to left. I wouldn't expect those of you that went left to right to say it's 48 inches. Those of you that went right to left, you'd say it's negative 48 inches. You're talking about a size. So a size is always a positive number. And so in that sense, we talk about the absolute value as being the size, and either zero or positive. Now with that notion of the size, if you think about the distance between real numbers, there's two ways that we can look at it. You can say, okay, the distance between -1 and 3 is if we take 3 minus a -1 and we get 4. Or if we look at it as any a and b and put it in the absolute value, then you don't really care if b is bigger than a or not. You'll get the same number. So if it's 3 minus -1, you get 4. And if it's -1 minus 3, when you take the absolute value, you'll get 4. So the size of that difference is indicated by the absolute value sign. And so that's what that does, is it gives you a positive or a number or a zero that indicates what that line is. Okay, so I'm going to stop here, and we should be at the end of class here pretty well.